It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
Imagine you ask a machine to write a sonnet in the style of Shakespeare about a lonely Mars rover. It doesn't just produce rhyming couplets, it captures the iambic pentameter, the Elizabethan vocabulary, and a sense of profound cosmic melancholy. Now, what if I told you that this machine, at its core, is doing something deceptively simple? Something not much more complicated than the autocomplete on your phone, it's just predicting the next word, over and over again. The profound question we'll tackle today is, how do you get from "thank you for" to "shall I compare thee to a summer's day"? The answer, in a word, is scale. In this episode, we're going under the hood of the technology that has captured the world's imagination. Large language models, or LLMs, we won't just skim the surface. We will build our understanding from the ground up. We'll start with their ancestors, the simple statistical models of the 20th century. We'll dissect the revolutionary architecture, the transformer, that made today's scale possible. We'll walk through the two-act play of how these models are trained. And finally, we'll confront the strange and powerful consequences of making them unimaginably large, exploring the predictable power of scaling laws and the mysteries of emergent abilities. By the end of this episode, you will understand not just what an LLM is, but why its size makes it a fundamentally new kind of machine. To understand the revolution, we first have to understand what came before. Language models are not a new concept. They are the product of over 75 years of innovation, a long journey of trying to get machines to process human language. When you step back and look at this timeline, a clear pattern emerges. The entire history of language modeling can be seen as a relentless quest to solve one problem: how to give a machine a richer, more flexible understanding of context. The earliest attempts, back in the 1950s through the 1970s, were dominated by what we call symbolic or rule-based systems. This was an era of handcrafted logic. Computer scientists and linguists worked together to codify the rules of grammar and syntax into algorithms. A famous example is ELIZA, a program from 1966 that mimicked a psychotherapist by using pattern matching. If you typed, "I am feeling sad," ELIZA might recognize the pattern, "I am feeling X," and respond, "How long have you been feeling X?" Another was SHRDLU, a program that could understand commands within a simulated world of blocks, demonstrating an ability to resolve relationships between objects. These systems were clever, but brittle. They only worked in highly constrained domains and automated simple, predictable interactions. The paradigm began to shift in the 1980s with the statistical revolution. Researchers started to realize that it was more effective to have a machine learn the patterns of language from data, rather than have humans program them by hand. This led to the rise of the N-gram model, a cornerstone of statistical NLP. Think of an N-gram model as a person with an extremely short and rigid memory. An N-gram is simply a contiguous sequence of N words. A trigram, where N equals 3, trying to complete the phrase, "The quick brown fox jumped," can only look at the last two words, "fox jumped." It then scours its training data, a large body of text called a corpus, and calculates the probability of every word in its vocabulary appearing next. If "over" appeared after "fox jumped," most frequently in the training data, the model predicts "over." It has no concept of a fox, of jumping, or the sentence's overall meaning. It is a pure statistical pattern matcher with a tiny fixed window on the world. These models were simple, fast, and for short, frequent phrases, they worked reasonably well. By the 1990s, IBM's smoothed N-gram systems, trained on hundreds of millions of words, were outperforming the old rule-based approaches and setting performance records. But they suffered from two critical, related flaws. The first was data sparsity. If the exact phrase "fox jumped" never appeared in its training data, the model was helpless. It couldn't predict anything. The second was a complete lack of semantic understanding. It treated the words dog and puppy as two completely unrelated symbols because it had no concept of meaning. It was all syntax, no semantics. The next great leap forward came with the arrival of neural networks in the 2000s. This era introduced two transformative ideas. The first was the concept of word embeddings, popularized by models like Word2Vec from Google in 2013. Instead of treating words as discrete symbols, word embeddings represent them as dense vectors, long lists of numbers, in a high-dimensional space. This solved the semantic problem. Words with similar meanings were now represented by similar vectors. This allowed the model to generalize. Even if it had never seen the phrase, "the puppy jumped," if it understood the vector for puppy was close to the vector for dog, it could use its knowledge about the dog jumped to make an intelligent guess. This is what enabled the famous analogy: if you take the vector for king, subtract the vector for man, and add the vector for woman, the resulting vector is closest to queen. Language now had a geometric structure that captured meaning. The second key idea was the recurrent neural network, or RNN, and its more powerful variant, the long short-term memory network, or LSTM. We covered these in depth back in episodes 17 and 18. LSTMs were actually invented in 1997, but became prominent much later. These models were designed to overcome the fixed, tiny context window of n-grams. An RNN is like our n-gram model, but now it has a form of memory, called a hidden state. As it reads a sentence word by word, it keeps a running summary of everything it has seen so far. When it gets to the word jumped in our sentence, its memory contains a trace of the, quick, brown, and fox. This allows it to capture long-range dependencies. For instance, ensuring a verb at the end of a long sentence agrees with a subject at the beginning. By 2016, these models were state-of-the-art. Google Translate upgraded its entire system to use an LSTM-BASED architecture with an added attention mechanism, a way for the model to focus on the most relevant parts of the input sentence when generating a translation. This was a huge improvement. But RNNs and LSTMs had a fatal flaw for the coming age of big data and massive computation. They were inherently sequential. To process the 10th word in a sentence, you first had to process words 1 through 9 to compute the necessary hidden state. This created a computational bottleneck. It was impossible to fully parallelize the process on modern hardware like GPUs, which excel at performing many calculations at once. This sequential bottleneck placed a hard limit on how large and powerful these models could become, setting the stage for the next and most dramatic revolution. The history we've just traced was a story of incremental improvements, of solving one problem only to run into the next. The year 2017 marked a true paradigm shift with the publication of a paper from Google, titled, simply, "Attention is All You Need." This paper introduced the transformer architecture, the foundational technology for every major large language model today, from GPT-4 to Llama 3. The transformer's success is a story of architectural hardware co-design. The algorithm was designed for the hardware, and the hardware enabled the algorithm to scale to a point where entirely new capabilities appeared. To understand it, we need to look at two things: its brilliantly simple training objective and the revolutionary mechanism that allowed it to break free of the sequential bottleneck. At its heart, an LLM is trained on a single, simple task. Given a sequence of text, predict the most probable next token. A token is a word, or more commonly, a part of a word. The model is given a chunk of text, makes a prediction, compares its prediction to the actual next token in the text, calculates the error, and adjusts its internal parameters, its weights, to reduce that error in the future. This process is repeated billions of times. This is an autoregressive process. At inference time, when we use the model, it generates a token, appends that token to the input sequence, and then feeds the new, longer sequence back into itself to predict the next token, and so on in a loop, until it generates a special end-of-sequence token or hits a length limit. But why does this simple objective lead to such complex and intelligent-seeming behavior? The answer lies in the data. The training data is a significant portion of the public internet, a vast, messy, beautiful repository of human knowledge, logic, dialogue, and creativity. To get consistently low prediction error on this dataset, a model cannot simply memorize sequences of words. The number of possible sentences is effectively infinite. Instead, it is forced to learn a compressed internal representation of the concepts and the world described in the text. To accurately predict the next word in a scientific paper, it must learn an implicit model of physics. To predict the next word in a legal contract, it must learn the logic of law. To predict the next word in a computer program, it must learn how to code. The simple objective of next token prediction, when applied at a planetary scale, implicitly forces the model to create a world model. The reasoning we observe is not something explicitly programmed in. It is a skill the model had to develop as a necessary tool to become an excellent next token predictor. The transformer's core innovation was a mechanism that could process all tokens in a sequence at the same time, completely eliminating the sequential processing of RNNs. This mechanism is called self-attention. Imagine you're in a crowded room trying to understand a sentence being spoken. An RNN is like listening to one person at a time in a long chain, trying to remember what each person said. A transformer with self-attention is like being able to look at everyone in the room simultaneously and decide, for each word you are currently focusing on, which other words are most important to understanding its meaning in this specific context. For example, in the sentence, "The robot picked up the ball because it was heavy," the pronoun it is ambiguous. Self-attention allows the model to calculate that it should attend strongly to ball and not to robot. Resolving the ambiguity, it can make these connections directly, no matter how far apart the words are in the sentence. So how does it work? For every token in the input sequence, the model learns to generate 3 separate vectors: a query, or Q, a key, or K, and a value, or V. The query vector is like a question. The token asks, "Given my role in this sentence, what information do I need from other tokens to better understand myself?" The key vector is like a label on every other token. This is the kind of information I hold. The model then calculates an attention score by taking the dot product of one token's query vector with the key vector of every other token in the sequence. A high score means a strong relevance. These scores are then normalized into attention weights using a softmax function, ensuring they all add up to 1. Finally, the value vectors of all tokens are summed up but weighted by these attention scores. The result is a new, contextually rich vector for our original token, a representation that has been informed by all other tokens in the sequence according to their relevance. The crucial part is that this entire process, the creation of Q, K, and V vectors, and the calculation of attention scores, can be expressed as a series of matrix multiplications. This is exactly the kind of operation that modern GPUs are designed to perform with incredible speed and in parallel. By breaking the sequential bottleneck, the transformer architecture unlocked the ability to train on vastly larger datasets and with models containing hundreds of billions and now trillions of parameters. This is the breakthrough that enabled the era of large language models. So we have a powerful architecture and a simple objective. But how do we get from a blank slate to a helpful AI assistant like ChatGPT or Claude? This happens in a two-stage process, a kind of two-act play that separates the acquisition of raw knowledge from the shaping of a useful personality. The first act is pre-training. This is by far the most computationally expensive and time-consuming stage. A randomly initialized transformer model is fed a colossal, diverse corpus of unlabeled text. Think of a huge snapshot of the internet, plus a massive digital library of books. The goal here is not to create a useful product. The goal is to use the next token prediction objective to force the model to learn the patterns of language, the structure of grammar, facts about the world, and the latent reasoning abilities we discussed earlier. This process can take weeks or even months, running continuously on supercomputers packed with thousands of GPUs. The output of this stage is what we call a foundation model or a base model. It's an incredibly knowledgeable system, a powerful text completion engine. But it's not yet an AI assistant. If you were to ask a base model, what is the capital of France, it might correctly answer Paris. But it's just as likely to complete your question with another question, like, what is the largest city in Spain? It's simply continuing the pattern of the text it was trained on, without any specific instruction to be helpful or to answer questions. It has the knowledge, but it lacks alignment with human intent. The second act is fine-tuning, where we take the powerful but untamed foundation model and teach it how to be a useful and safe assistant. This stage uses much smaller, carefully curated high-quality datasets. The first step is often supervised fine-tuning, or SFT. Here, the model is trained on a dataset of high-quality examples of prompts and ideal responses, often written by human labelers. For example, the dataset would contain pairs like prompt, write a short poem about the moon, ideal response, silver orb in velvet night. This teaches the model the format of following instructions and providing helpful answers. A more advanced and powerful technique, pioneered by OpenAI, is reinforcement learning from human feedback, or RLHF. This is a three-step process. First, we take a prompt and have the SFT model generate several different responses. Next, human labelers rank these responses from best to worst. This ranking data is then used to train a separate reward model. The reward model's job is to look at a prompt and a response and output a score predicting how a human would rate it. Finally, the LLM is further fine-tuned using reinforcement learning algorithms. The LLM is treated as an agent that plays a game where its action is generating a response. It gets a reward from the reward model, and it adjusts its own parameters to generate responses that will maximize that reward. This entire fine-tuning process, especially RLHF, is what shapes the model's behavior. It's what teaches it to be conversational, to refuse to answer harmful requests, to admit when it doesn't know something, and to generally act as a helpful, harmless, and honest AI assistant. Much of what we perceive as the AI's character or personality is a direct result of the data and human preferences encoded during this alignment phase, not the raw knowledge from pre-training. This two-act structure is incredibly efficient. One massive, expensive pre-training run can create a foundation model that is then cheaply and quickly fine-tuned for many different specialized applications. We've now established how these models are built, but the central theme of this episode is scale. What actually happens when we make these models bigger? More parameters, more data, more computation. It turns out the answer is twofold. Some improvements are remarkably predictable, while others appear as if from nowhere. The predictable path is governed by what are called neural scaling laws. In 2020, researchers at OpenAI published a groundbreaking paper on what they called neural scaling laws. They demonstrated that as you increase three key factors, the number of parameters in the model, the size of the training dataset, and the amount of compute used for training, the model's performance on the next token prediction task improves in a smooth, predictable power law relationship. This was a monumental discovery. It transformed LLM development from a research-driven art into a more predictable, engineering-driven discipline. It meant that progress wasn't random. If you could secure a larger budget for a bigger supercomputer and more data, you could be confident that you would get a better model. This is what justified the massive capital investments required to build today's state-of-the-art models and fueled the GPU arms race. Later work, notably the Chinchilla paper from DeepMind in 2022, refined these laws, showing that for optimal performance, model size and dataset size needed to be scaled up in tandem. This research revealed that many earlier models, like GPT-3, were actually undertrained for their size. They had too many parameters for the amount of data they saw. But alongside this predictable improvement, something strange was happening. As models crossed certain thresholds of scale, they suddenly developed capabilities that were simply not present in smaller models and could not be predicted by extrapolating from their performance curves. These are called emergent abilities. An ability is defined as emergent if a model's performance on a specific task is near random for smaller models. But then, once the model reaches a critical scale, performance spikes sharply to well above random. Examples of such abilities include performing multi-step arithmetic, answering questions that require combining multiple pieces of information, and one of the most important discoveries, chain-of-thought reasoning. Researchers found that simply adding the phrase, "let's think step by step," to a prompt could dramatically improve an LLM's ability to solve complex reasoning problems, but only for models above a certain size. Smaller models didn't benefit. This ability to break down a problem and show its work seemed to emerge from the scaling process itself. The idea of emergence is tantalizing, but it's also concerning. If capabilities can appear unpredictably, we might accidentally scale a model into having dangerous abilities we didn't foresee. This has led to a fascinating and crucial scientific debate. A compelling counterargument, notably from researchers at Stanford, proposes that these emergent abilities are an illusion or a mirage created by our choice of evaluation metrics. Here's the argument. Many of the benchmarks that show emergent abilities use harsh, nonlinear metrics like exact string match. Imagine you're testing a model on 4-digit addition. The exact match metric gives the model a score of 1 if its answer is perfectly correct, and 0 if even a single digit is wrong. A smaller model might get the first 3 digits right but mess up the last one. Its score is 0. A slightly larger model might get all but the last digit right. Its score is still 0. As the model scales, its underlying ability to do math, its per-digit accuracy, improves smoothly and predictably. At some point, it crosses a threshold where it's likely to get all 4 digits correct. At that moment, the exact match score suddenly jumps from 0 to 1, looking like a sharp, emergent leap in ability. The mirage argument states that if you instead use a smoother, more continuous metric, like simply measuring the percentage of correct digits, the sharp jump disappears. Performance improves gradually and predictably with scale. This debate is not just academic. It's about how we understand and predict the progress of AI. It suggests that to truly understand these systems, we need to be as rigorous about developing our evaluation methods as we are about developing the models themselves. The very tools we use to measure reality can shape our perception of it. Now that we've journeyed from engrams to transformers and from scaling laws to emergent abilities, let's ground ourselves in the present day. How should we think about the LLMs we interact with, and what does the current landscape look like? A core part of AI literacy is learning to resist our natural tendency to anthropomorphize these systems and instead understand them for what they are: complex statistical machines. Let's address some of the most common misconceptions. First is the myth that LLMs understand language like humans do. The reality is, they are masters of statistical pattern matching, not genuine comprehension. When an LLM processes a sentence, it's not forming a mental image or a conceptual understanding. It's navigating a high-dimensional vector space of learned relationships between words and ideas. This is the core of the famous stochastic parrots critique. They are brilliant mimics of the patterns in human-generated text, but they lack true meaning or communicative intent. Second is the myth that LLMs are always learning from your conversations. The reality is, most deployed LLMs are static. Once they are pre-trained and fine-tuned, their internal weights are frozen. They do not update their knowledge or learn from individual interactions. The memory you experience in a long conversation is simply the model being fed the entire chat history as context for each new turn. Third is the myth that LLMs have perfect factual recall. The reality is, an LLM's knowledge is stored distributively and probabilistically across its parameters. Not like a database, this can lead to hallucinations, the generation of plausible-sounding but entirely false information. Furthermore, their knowledge is frozen at the point their training data was collected, creating a knowledge cutoff date. Finally, there's the myth that more parameters always mean a better model. The reality is, while scale is a primary driver of capability, it's not the only one. The quality and diversity of the training data, the model's architecture, and the quality of the fine-tuning process are immensely important. A smaller model, trained on very high-quality, specialized data, can often outperform a much larger, more general model on specific tasks. The modern LLM landscape is defined by a dynamic and sometimes ideological tension between two approaches: proprietary and open source. On one side, you have proprietary or closed-source models. These are developed by companies like OpenAI with their GPT series, Anthropic with the Claude family, and Google with Gemini. These are often the most powerful state-of-the-art models. But their inner workings, their architecture, training data, and model weights are kept as trade secrets. Access is typically provided through a paid API. The argument for this approach often centers on safety through control. By limiting access, companies can better prevent misuse. On the other side is the vibrant open-source movement. Propelled by releases from companies like Meta with their Llama series and Mistral AI, as well as contributions from research collectives and startups like Alibaba with their Qwen series and DeepSeek AI, this movement champions transparency and accessibility. Open-source models have their weights, and often their code and details about their training data, publicly available for anyone to download, modify, and use. This has dramatically accelerated the pace of innovation and democratized access to powerful AI, allowing researchers, startups, and even individuals to build upon the state-of-the-art. The argument here is for safety through transparency. Broad community scrutiny can identify flaws and biases more effectively than a small, closed team. So, we've traveled from the simple, memoryless world of engrams to the vast, parallel, context-aware architecture of the transformer. We've seen how a model is built, first learning a general model of the world through pre-training, then learning how to interact with us through fine-tuning. And we return to our central question: how does a simple next token predictor write a sonnet about a Mars rover? The answer is that scale transforms quantity into quality. When a system designed to find statistical patterns is scaled up and fed a dataset that contains nearly the sum of human knowledge, the patterns it learns are not just about which words follow others. They are the patterns of logic, the patterns of causality, the patterns of creativity, and the patterns of reason itself. The simple objective, at an unimaginable scale, forces the emergence of complex behavior. But this incredible power brings with it incredible challenges and responsibilities. How do we ensure these models are safe and aligned with human values? What happens when this capability extends beyond text to images, audio, and video? Next time, we officially enter the world of generative AI. We will explore the brilliant dueling architecture of the Generative Adversarial Network, or GAN, where two neural networks, a forger and a detective, play a cat-and-mouse game to create impossibly realistic images. And we will look at the powerful and probabilistic variational autoencoder. We are moving from understanding and replicating language to the art of pure creation.
You've been listening to AI Deconstructed. Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.